Hello again. It has been a while since we last chatted like this. I had a spring break. I hope maybe you had a little bit of a break from your studies as well. We got one more section to cover in this whole topic of circles. And it's kind of interesting. I didn't include this in the packet I sent out to you of all the theorems because I wasn't going to cover this before the SBAC. But once they canceled the SBAC and sent us home, I wanted to cover it. It's really interesting. It's a little bit overwhelming at first, and there's only 3 theorems, but when you see what we're going to go through today, it's a little bit daunting, but I think it's really worth knowing. So let's just get started. I'm going to actually use my notes quite a bit today, and I'll switch back and forth between those and the whiteboard, but I'm going to spend a lot of time in my notes because there's a lot of really good drawings that we can look at, and then I'll mention a couple things on them. So if you look at the screen, you'll notice that we've talked about tangent lines. Those are lines that touch the circle only once. We've talked about chords, which are segments that connect 2 ends of the circle and that lie inside the circle. Today we're going to look at the third one, which is called the secant. And a secant is kind of like a chord that's all grown up because it extends outward in all directions. You can put arrows on the end of that, and that would be a good picture of what a secant looks like. So we're going to take a look at how 2 secant lines intersecting or interacting with each other create a whole set of kind of interesting and unexpectedly complicated situations for us. Okay, so the theme here is secants. So let me go down and show you this first situation here. And I know that there's going to be a little bit, it's going to be a little bit weirder because I'm not going to draw so much. But the first situation that will be of interest to us is when we have 2 secants that intersect inside the circle. So you can see this on the left-hand side. The 2 lines intersecting inside the circle, and then there's another case where the 2 secant lines intersect outside the circle. So there's not actually any intersection inside, it occurs outside. Okay, so get that picture in your mind. Intersection point inside the circle, intersection point outside the circle. And this is the theorem that I want to give you. And we're going to talk through what this means. But I want to highlight this word and this word and this word and this word. So we're looking at what happens when 2 lines intersect inside a circle, 2 secant lines intersect inside a circle, and it's the angle, we're talking about the angle being formed. So if you go back up to this example right here, let me pull this up. I think I can do this in a way that might be interesting to us. I'll pull this up. What we're really interested in here is this angle here, and of course this angle here. Now we know that they're vertical angles, so they're going to be congruent, but we're looking at what that angle is based on the measure of this arc and the measure of that arc. Okay, so keep that in mind. And the theorem goes like this. Again, this is a new theorem, so you don't have this, but I did upload a new, I put as an addition to the previous theorem list that I gave you, and then I've got a full theorem list as well. So you can go on the website and you can look and download these if you want. The angle formed when the 2 lines intersect inside a circle is the average of the arcs. That's odd. Well, let's take a look at this problem right here. And I'm going to probably do this again with screenshots more than the whiteboard. So the question is asking us for this angle right here. And by the way, this is also going to be x, again, because they're vertical angles. So if you look at this, you'll notice that these angles actually lead to 2 arcs. The x on this side leads to that arc, and the x on that side leads to that arc. Now, that doesn't mean that either of these is 90 or 200. What I'm saying is those are the angles and those are the arcs. Okay, so what we do here And I'm going to write this, bear with me just for a second. I'm going to take this off the screen for a second, write something, I'll come right back to you, okay? So this is what I wrote on the screen. The measure of angle x is the average, that means add them up and divide by 2, of the two angles. So this is 290 here. Half of 290 is 145. And that's what x measures. Okay? So add them up, divide by 2, not the worst thing in the world. Okay. Now here's another problem I want you to try. I think I might actually take this and put this onto my whiteboard. So take a good look at this, and then I will transfer this onto the whiteboard so you can follow. So you have to be a little bit patient with me here while I do this. We have a circle here, and we have some lines. One goes through here, one goes through there, and one goes there. There is a center right here. Oops. Center right there. We've got 2x here, 40 degrees there, 55 degrees there. And we're trying to find the value of x. So let's find x. You ever seen that joke where it says find x and you're like, oh, it's right there, found it. Hey, that's not what we're doing here. Okay, so what are you going to do here? Well, here's the problem. This 2x is sort of sitting there with this arc, and then obviously, 2x sits here as well, sits there for that arc, but that's a bit of a problem. I'm going to show you two thoughts here, and we'll see if this works out. Here's what I'm guessing. This 55-degree angle is an inscribed angle, right? That cuts off this arc right here. So this has got to be 110. You saw that in the last section. So therefore, 110 plus 40 equals 150. Half of 150 equals 75. So I'm going to say this is 75 degrees right here. If that's 75 degrees, this has to be 115, right? Or no, sorry, 105, excuse me. 105 to get us to 180, that makes a straight line. So now I can write 2x equals 180. Ah, just kidding. 2x equals 105, and x equals 52. That's kind of much, wasn't it? Let me remind you, we had this. From 55 degrees, we found 110. We added those up, cut them in half, and got 75 for this angle right here. And then 75 plus 105, we know makes 180. So 2x equals 105, x is 52.5. Now, I'm going to show you something else. I think this is interesting. If this arc here is 40, then I think we can figure out what this angle is right there. Do you? It's an inscribed angle that cuts off a 40-degree arc. I think that's 20 degrees. Which means 20 plus 55 makes 75, which means this one has to be 105. And it works out that way as well. So at this point, I mean, we have a lot of different ways we can tackle these kinds of problems. And I don't care which way you do it. I just want to show you that there's a lot of ways to do it. All right, let's move on. Case 2 is a little bit trickier. So remember, the first case was the lines intersect inside the circle. Now we actually have two different ways that the lines intersect outside the circle. The first one is this one right here. I'll make this a little bit bigger so you can see it. The first one is when we have two true secants. That means they both intersect the circle twice. The second case is when you have one secant and one tangent. And I got news for you. There's actually a third case where they're both tangents. So what I'm saying here is anytime you've got two secants that intersect outside the circle, the two lines can do one of three things. They can both be tangent. One could be tangent, one could be a secant, or they could both be secants. The good news is the way we find the angle, and by the angle I mean the angle formed where the two secants intersect, is the same for all three of these. So let me scroll ahead to the theorem, then we'll look at some examples. So here's the theorem. And I'm going to highlight a couple of things. First of all, I'm going to highlight angle and arcs. Same thing we saw before. We have two lines intersecting outside a circle, but this time the measure of the angle is 1/2 the difference of the two arcs. When they're inside, you add the two arcs and divide by 2. When they're outside, you subtract the two arcs, obviously bigger minus smaller, and then you cut that in half. So let's take a look at a couple of these examples and see how this works. And I think what I'm going to do is I'm going to let you look at that for a second, but I'm going to transfer this over to the whiteboard again so I can draw it. So I want you to watch this real carefully. I want to find angle X, just down here in the lower right. XYZ is this first arc right here on the near side, so to speak, and ABC is on the far side. So let me copy that over to the whiteboard, and we'll see how this works. I'm going to draw a circle. And now we're going to have these two lines. Oh, I take it back. Excuse me. They're both secants, right? And then we'll label some of these measurements. So this is going to be X here. We've got, I'm just going to simplify it. This is going to be 50 degrees here. This is 140 degrees here. That's the whole problem. Now I go back and show you where it came from. But the only thing that really matters here is that we have 50 degrees on the near side and 140 on the far side. Okay. So what do? Well, X is now going to equal 1/2 of the difference between these. So now it's 140 minus 50, 1/2 of 90. That's 45 degrees. X is 45 degrees. So, I mean, I know that this is a little bit complicated at first, but really all you're doing is you're adding up arcs or you're subtracting arcs, and then you're cutting them in half. Okay? So, that's the start of it. I have another example. Yeah, there's another example. Let's do this one. This will be kind of fun. We'll just talk through this one together, though. Maybe what I'll do a screenshot. I'm just so technologically adept here. Okay, I do the screenshots because I can now write on it. So if I want to find X here, this is a little bit tricky because now I have a tangent and a secant. But I can see here that the tangent and the secant together are cutting off this arc for sure, and then also that arc. But I don't know what that arc measure is. What I do know is this. I'm going to take it off the screen for a second. Bear with me. I do know that 187 plus 141 plus, we'll call it Y, equals 360. Okay, so this is going to be Y here. I didn't label it X because we already got X there. If I add up all three of these arcs, I know I'm going to get 360. So I just subtract 200, 320, 328 from 360, and I'm going to get 32. I got 32. So now X, the angle that cuts off these two arcs, is going to be 1/2 of the difference between those. So let me write this again over here. x equals 1/2. The difference, 141 minus 32, half of, I'm going to say 89, which is 44.5. Does that look right? I think that looks right. So it's a little bit harder for sure, but also all you do is looking for arcs. Find the two arcs that are cut off. As long as the vertex, the intersection point of the secants is outside the circle, you subtract the two arcs, take half of that, and that's going to be your angle. Okay? So that's our first and second theorem, actually. Now, we're going to go to a third theorem for the day, and this is going to be one theorem, but it's got lots and lots of versions on it. So let me see if I can get caught up here. And what I want you to look at now is, instead of angles, I want you to look at segments, lengths of segments. So what we have here, I think I'll snap this real quick so we can talk about it. We have a case where these two, okay, they are chords, in fact, the way it's drawn here, but they're part of secants. They intersect inside the circle at this point right here. So I want you to picture you're standing at that point, and you're kind of spinning around looking at these lines that are going out towards the edge of the circle. What do you see? Well, when you look along one line, you probably see the numbers 3 and 9, right? You're 3 units away from the circle one direction, and you're 9 units away the other direction. But what if you look at a different line? I'm changing colors here, so another line. Well, if I look the other way, now I've got 6, and I've got this unknown A. Okay, so 3 one way, 9 the other way, along one line. Pick the other line, it's 6, and there's some unknown distance A. Okay, that's what we're looking at. And what I'm going to do is I'm going to jump right to the theorem here, and then we'll walk through this. Look carefully. Again, I'm going to pick a couple of keywords. The product of any two segments lengths to a side of the circle is the same. What? The product of two segment lengths to a side of the circle is the same. Let's go back and look at this. What do we have? Well, I have so lengths to the edge of the circle, 3 times 9. Obviously, that's 27. But it's the same as if I go the other direction. That is 6 times A. Okay? So now, I get tired of using my mouse here. Divide 6, A equals 4.5. And this is where we get our final answer. So what I'm going to do is I'm going to stand up at whatever point I'm at the intersection point. I'm going to look along each line at the distance to the edges of the circle. There's got to be 2 points of the circle because every secant intersects the circle twice. And I'm just going to take the distance one direction, distance the other direction, multiply them together. And then do it the other way, and that's how I'm going to find the unknown side. Okay, so let's go back and look at the other case, or second case. This one is probably the hardest. So I want to, I'm actually going to turn this on to the whiteboard so I can walk you through this one. This one is, I think it might be the hardest one. We're going to take a circle here. And I've got a line. I'll just take it all the way through, it doesn't really matter. Lines like that. And I'm going to say that this is 9, this is 11, this is 10, this is X. Okay. And we now have to figure out what x is. And I'm telling you, this is the one that more students miss than any other problem in this entire section, right here. So here's what we're going to do. We're going to stand right here, and we're going to look along each line towards the edges of the circle, and we're going to take the measurements towards the edge of the circle. So I'll give you the first one. This one's going to be easy. What's this length right here? 9. Cool. Now, look along the same line. What's the distance here? And if you want to say 11, don't, because it's not 11 from this intersection point to the edge. That distance right there is 20. So 9 times 20 equals 180. You see how easy this is to get wrong? It's okay, I got you. So now let's do the other one. What does it look like when I go this way? The first one is 10. I'll do it over here. But now from here all the way to here, it's not x. What is it? It's 10 plus x. And that product also has to equal 180. That's the theorem. The product of the two segments to each side of the circle is the same. So if the first one, 9 times 20 equals 180, and the second one, 10 times 10 plus x equals 180. So here we go. 100 plus 10x equals 180. Subtract 100. Hey, algebra. 10x equals 80. Divide 10. X equals 8. 8. Guys, there's nothing that connects the 11 to the 8. That 11 isn't really an 11 as far as we're concerned. The 11 is part of 20, and the 8 is part of 18. So I'm telling you, this is one of the hardest kinds of problems there is to keep straight. This distance plus this times that distance equals this distance times that distance. Okay? I got more examples coming for you. Let's just go back and finish this off. Because the third case is, I don't know, a little bit complicated-ish looking, but it's not actually that bad. So let me start. I'm going to take the screenshot here, and we'll see if we can walk through this. So again, we're going to be looking at this point right here. And on one hand, well, this side's not too bad. We're going to multiply 12 times that whole length. I'm going to transfer this over to the whiteboard so I can show you. Just a second. In fact, let me do that right now. So let me pull this up. I got to believe there's got to be an easier way to do this, but why would I want to make things any easier for me, right? Yeah, that's not even close. That's all right, we'll make it work. Okay, so what I'm suggesting here is that we have an 18 here, a 12 here, and an x plus 9 here. So I can write the first part of this pretty reasonably. Starting from here, I've got a length of 12, and then this whole distance is not x plus 9. It's 12 plus x plus 9, which is, well, let me make it a little bit better here. It's x plus 21. Take a good look at that. It's x plus 9 plus 12 for this long path right there. Now, what does that equal? Well, I know that one distance to the circle is 18. But, oh boy, what about the other one? It's also 18. So when you have a tangent, then this leg counts twice. okay? It counts twice. So this is our problem, and this is still not too bad. I'm going to show you eventually where the really difficult parts of this is. But let me just do some distributive property here. 12x plus, oh boy, 252. How did I do? 12 times 21, ha, crushed it, equals 324. Okay, subtract 252. And 12x equals, I hope it comes out, 72, x equals 6. So this leg right here, 6 plus 9 makes 15. Now, you might be tempted to think, wait a minute, 12 times 15 doesn't make 18 squared. You're right, but 12 times 27 does. Okay? So with a tangent counts twice, and you're going to square that, that one tangent length. All right, so let's go see if I can give you a couple of examples to do on your own. I feel like we did that one already. Oh, we did that one too. Oh, we did that one too, look at that. Oh, by the way, but this one here, notice it said find FD, didn't ask for X. So we found that X equaled 6. That makes this chord length, DE, 6 plus 9 equals 15, and it makes the entire secant length, 15 plus 12 equals 27. So make sure you're okay with, remember, we've talked about don't just solve for X and think that's your answer. Don't just, in this case, think that the chord length, DE, is the answer. We're actually finding the length of the secant, which is FD. So let me copy these over and we'll wrap this up. It wasn't maybe as bad as we thought. I thought it might be a little bit worse than that. Maybe it was pretty bad. Here is your set of assignments for the next few days. So today we're going to look at page 456, which is going to be out of your book. And then there's two pages on the website that I'm going to want you to download and complete and turn in. Remember that the CUDA forms always come with with answers. The practice 12, and actually I need to clarify something here. We're only doing, whoops, just kidding. We're only doing B. We're not doing C here. And that one doesn't come with answers, but I made answers for you. So play around with secants. They really aren't, they're not that bad. I kind of like them, but I tell you what, they're really, really easy to mess up. So be careful, be cautious about that. But listen, here's some of the good news. So this is for Wednesday, April 15th. Thursday, Friday are the review days. Thursday is going to be CUDA. Friday is going to be the practice B. Monday, I'll have a review assignment for you. You need to look on the website for it, but I'll email it out to you as well. Monday will be a review, and your test will be available starting on Monday in next week's schedule. And you will have until Wednesday, April 22nd, to finish your test. So today is the last day of new stuff for a week. Review, 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 study, test. And this will go on your fourth quarter grades. Fourth quarter grades will count. Remember, if you have not heard already, you will have an option of taking it for credit or no credit. And not really pass fail, because if you get no credit, it just means it's like didn't even exist. It's not an F. Your grade point doesn't suffer. If you want to take this class for credit, you'll get credit on your transcript, but nothing on your GPA. Or you can take it for letter grade. And if you want to get honors notation, you'll have to take it for a letter grade, but that'll all come out from Mr. Goodnight in the next few days. So anyway, we're moving into fourth quarter. That's all I got. I will probably talk to you next on April 23rd. as we move in and start looking at 2-dimensional and 3-dimensional shapes. And that'll be kind of interesting. It'll be a nice change. There will be some triangles and circles, but not really quite like we've done before. So anyway, I miss you guys. Be well, work hard, ask good questions when you're stuck, and I will talk to you next time.